it's element 39 again and welcome to my new video. Sorry, it's been a little while, school's been busy. Anyways, I hope you like this video and let's dive straight in. Computer chips are arguably one of the most important inventions of the human race. They are at the heart of every single object powered by electricity that we see nowadays and are at the core of the newest developments in technology. These chips are made from silicon wafers, which undergo a metamorphosis into the small, light, and powerful microchips that allow so much to function in our modern world. In the beginning, computers were people working behind desks with a calculator, pencil, and paper. These people were called computers since they computed or calculated sums, usually for a larger and much more complex problem. At first, the computers were mostly male, since education was restricted to them. Ever since the Renaissance, they were hired and paid by other mathematicians to help crunch data and perform calculations, usually for predicting the positions of the planets. Many mathematicians and astronomers at the time worked this way. Kepler, an eminent mathematician and astronomer of the 16th to 17th century, was known for often temporarily assisting others as a computer until he came through a breakthrough of his own. A growth in education and the ever-increasing numbers of the middle class in the 19th century had produced many young women that were trained in maths. Most of these computers were women since they were cheaper. They could be paid at less than half the cost of their male counterparts. This meant that it was more economical to hire these women instead of their male counterparts. The first human computers worked for the French mathematician Alexis Claude Clairaut, who employed the astronomer Jerome Joseph Lalande and a clockmaker's wife Nicole Reine Lepaul. They worked in predicting the date in which Halley's Comet would be closest to the Sun, thus proving that gravity could be used to predict the orbit of objects in outer space. Since the calculations required would be too large for any one astronomer to do, he hired the two to assist him. This proved to be the start of the human computer age. These early computers were essential to a number of disciplines. Major banks, universities, and governments started hiring these women in swarms since they were cheap and could be mass hired. Dr. Cecilia Payne, who hypothesized and later proved that stars are mostly hydrogen, discovered that, to her dismay, the most advanced jobs for a woman in astronomy was as a computer during her time at Harvard in the early 1900s. In fact, being a computer was a highly regarded job against many educated women. Some even offered their services for free in order to win the job. In the Manhattan Project, there were many calculations to be computed, from the flight paths of the nuclear missiles to the unfortunate incident with the Demon Core, where one of the computers was asked to calculate the net radiation dosage of each person in the room. These computers were a mix between the wives of the scientists involved in the Manhattan Project and a hired group of women with degrees in mathematics and physics. They became the first operators of ENIAC, the early computer, after it was introduced. At NASA during the space race, female computers were employed in large numbers who confirmed the calculations produced by their higher-ups, even until the introduction of the first machine computers there. In fact, John Glenn, one of the astronauts in the Mercury missions, asked the computer, Katherine Johnson, to run the numbers again since he and many others believed that the machine-calculated result was untrustworthy. It was only when the computer became more advanced and more available did the age of human computers stop. From then on, human computers progressed in leaps and bounds. The creation of solar transistors, integrated circuits, and the invention of processors scaling up to the very large-scale integrated circuits have allowed computers to progress to what they are today. Now, one microchip the size of a fingernail has the same computing power as ENIAC, the early computer, which could calculate sums 2,400 times faster than a human. The computer that took the astronauts of Apollo 11 to the moon, though impressive, is hardly any comparison to the modern smartphone, which is 100,000 times more powerful. The most powerful computers of now may be obsolete within a decade with the fast rate of development that technology has over the past few decades and the continuing influence of Moore's law, although the latter theory has been strongly contested. Computers function because of the processors inside them, which are small silicon chips we call microprocessors. These computer microchips are made on silicon wafers of an extremely high standard, with a dopant added in to make the wafer either more negatively or positively charged. The silicon is often sourced from quartz instead of the usual sand that is used to make glass because it is a more dense form of silicon and has less impurities. The quartz is melted down in the presence of carbon and cooled to make 99% pure silicon. Here, two reactions are happening. In most cases, the oxygen in the silicon dioxide would combine with the carbon produced from the burning of the fuel to make carbon dioxide and pure silicon. However, carbon monoxide and silicon carbide are also produced as the process is not perfect and are left over as the byproducts. This is then either thrown away or in some cases purified again in the next batch where the process will repeat again. The aim of this purification is to make sure that the silicon is as pure as possible for use in the manufacturing process of the silicon wafers, as impurities may interfere with the function of the chip and react with the dopant. The silicon is then further purified into a polycrystalline silicon via a process known as the Siemens-Wiefhaven process, developed by the German company Siemens. The 99% pure silicon produced in the last step would be first heated to 325 degrees C in the presence of hydrochloric acid. This leaves the hydrogen gas being produced, as well as trichlorosilane, as well as the impurities reacting, leading to the production of iron 3 chloride, aluminium chloride, and silicon tetrachloride. Since they are all gases with different boiling points, they are cooled one by condensing each gas into a liquid until only the trichlorosilane is left. This is then converted back into the silicon, leaving extremely pure silicon in its wake. However, this silicon is polycrystalline, meaning that it is composed of many smaller crystals which have different crystal structures. This means that the silicon needs to be processed again to make monocrystalline silicon. The silicon is melted again with outside sources of contamination removed until it is liquid. Usually this is done in an argon or atmosphere in the absence of any oxygen via induction heating in a crucible. Once the silicon is molten, the dopants will be added into the silicon with the crucible rotated to ensure an even distribution of dopants suspended throughout the crystal structure. Usually, boron is added into the silicon to make it more positively charged, while arsenic would be added to make it more negatively charged. Aside from boron and arsenic, phosphorus, gallium, and antimony are also used as dopants. While the silicon will be cooling down, the dopants would start to move around in the crystal lattice of the silicon, occupying empty spots in the lattice and settling in between the spaces in the lattice, and exchanging places with the silicon atoms in some cases. These dopants create little recessions in the crystal structure of the silicon, where they occupy a space instead of the usual silicon atom. However, most times, there will be an imbalance in terms of the charge, either that they have too many electrons and some are left flying around, or they don't have enough and are left with a gap in one of the electron shells. This means that the chip would either have a slightly positive or slightly negative charge. Another process, known as the Joukowski method, is performed. It was accidentally discovered by the Polish scientist Jan Joukowski, who accidentally dipped his pen in molten tin and got a small tin crystal from it that resembled a melting cylinder. This is when an ingot of similarly pure silicon is used as a nucleation seed for the crystallization of the silicon in the tub, changing it from a polycrystalline form into a monocrystalline mass. The silicon's temperature will be lowered to just below the melting point on the metal and be slowly pulled out of the molten vat while it spins until it grows into an ingot. Ultimately, the silicon would be heated locally via an induction coil which would run up and down the length of the crucible. A seed crystal would be placed at the start where the heated coil would melt the silicon, which would solidify with the same crystal structure as the source crystal. This is called rapid magnetic induction heating, and much research is being carried out on it. The induction coil would use radio frequencies and microwaves to heat the silicon almost instantly, which meant that there would be less time dedicated to the production of the silicon ingot, the basis for the wafers. The size and diameter of the ingot is determined by the pulling speed. The quicker this is, the slimmer the silicon ingot will be. This process is also used to make other monocrystalline metals such as platinum and gold and synthetic gemstones. Usually, in the production of 300mm diameter wafers, the pooled ingot would have a diameter of 400mm and a height of 1 to 2 meters. Now that the base material for the silicon wafer has been made and refined, the process starts on making the wafer itself. Usually, the ingot of silicon obtained from the Chemistria process is a little larger than the wafer diameter, since the silicon crystal cylinder produced would not be perfect for a number of reasons. Due to the rotation of the crucible while the Chemistria method is performed, the surface of the ingot would also be slightly distorted with bumps on the surface. This means that the cylinder would need to be polished to the desired diameter with a large margin of error to assume that all of the wafers would be equal diameter. Both distorted ends of the silicon ingot would be chopped off and usually thrown away, though if the silicon is pure enough, it will be melted and recast. After this step, the cylindrical image would have a mirror shine to it. Polishing process produces a lot of heat. The silicon is usually cooled with water while being ground. Then, the silicon wafer has a small identifying edge or indent cut in it as a positioning indicator for identifying its purpose, as well as giving the robot a calibration position to set the start and ending point. Wafers with diameters of 200 millimeters and above would usually have an identifying notch carved into the wafer, while wafers with diameters under that will have flat carved into them. Since the silicon wafer can be in many different orientations, this information would need to be included to avoid confusion. The different crystal orientations would also lead to the wafer shattering in different ways, which can be a useful test for people who have many wafers on hand. After the silicon ingot is cut and polished, it is cut again into the desired shape of the wafers. This cannot be done with the traditional way with one sword cutting the silicon like one cuts a steak, because this process is inefficient and slow. Instead, the silicon is cut all at once, like multiple wire saws all working at once to cut a block of wood into small pieces. The strands of the saw are covered with diamond dust, giving it extra abrasive and cutting power to make sure that the wafer can be cut faster. Then, the silicon wafers are rounded off. This is not only because the silicon of this quality is prone to shattering and chipping, but because it would ensure the even coating of the photoresist, which would be used later in the manufacturing process. If the wafer had right angle sides, which is the case before polishing, there would be a relative abundance of ink towards the edges called the edge crown. This would mean that the details that were to be printed towards the edge of the wafer would not be properly developed, as it would require an excess of UV light to develop there. After this, the silicon wafer is usually branded with the number that proves crucial information about the wafer, such as the vendor, the batch number, the identification number, and its crystal orientation. This is also the same process in the manufacture of the solar panels, particularly of the solar cells in them that allow the panels to work. However, the purity difference between the silicon used for solar panels compared to the purity required for the silicon wafers is large. The silicon solar cells only require 6 nines with a purity of 99.9999%, whereas the purity required for the silicon wafers used in the silicon microchip manufacturing process needs 10 to 11 nines of purity, which is 99.9999999 to 99.9999999% purity, a large difference. The difficulty in producing and purifying silicon to this standard is what makes the production of silicon wafers largely concentrated in a few companies and suppliers around the world. Currently, the largest producer of these silicon wafers is China, due to a growing demand for renewable energy there. The silicon wafer is then roughened on one side while polished on the other. This is a part of a process called backside roughening, where a certain side of the silicon wafer is roughened. This is done in order to make the wafer thinner as well as to polish it so that all the impurities would mostly be located on the rougher side of the silicon wafer, as well as helping identify the side on which photoresist would be applied and the photolithography performed. Later, a layer of silicon dioxide would be applied to the silicon wafer. This is also one of the reasons why silicon is used so widely as a semiconductor. For every 1,000 free bonds the silicon has, the silicon dioxide can bond with 999 of them. This is an important ability that the semiconductor material should possess, and is one of the conditions researchers consider before pushing it for further research. This is also one of the reasons why germanium is getting a comeback as the source material for making the wafer. For every 1,000 free bonds on the surface of the germanium, 999 can be bonded to with germanium dioxide. The wafer is then pushed on to the next step, which is to cleanse it in 3 different baths. The initial cleaning bath and then an acid bath, which would wear down the surface of the wafer, smoothing it. There, a special reaction occurs between the nitric acid and the hydrochloric acid at the bath, eating away at the silicon and cleaning any impurities or organic matter that may have been on the surface of the chip, such as dead skin cells or any bacteria or viruses that may have been on the surface. Bacteria at their smallest are 200 nanometers wide, which is why workers who work at the factories often wear full body suits, masks, and gloves when handling the chip. If a worker there wants to smoke, they cannot enter the factory until 30 minutes after they smoke. The particles in their breath would affect the cleanliness of the factory and the environment in which the wafers are being processed. This also means that any imperfection on the surface of the wafer itself must also be smooth and perfect to that degree. To achieve this, the chip then needs to undergo a process known as CMP, or chemical mechanical polishing. The chemical mechanical polishing process uses a corrosive chemical slurry as well as an abrasive to make the surface of the silicon wafers smoother. Usually, the silicon wafers will be loaded onto a carrier which have measures put in place to make sure the wafers would not slip from the carrier. This would be achieved by using vacuum suction instead of adhesives, which would leave a residue on the surface. As a bonus, the vacuum would help with removing and keeping the surface of the wafer clean. There would also be a plate with a pad placed on top where the slurry and the abrasive would be deposited onto its surface. The carrier would then slowly be lowered onto the rotating surface of the plate where the slurry and the abrasive would start doing the work, smoothing out the surface of the silicon wafer until it is almost perfectly smooth. Depending on the diameter of the chip, the wafer would be polished either on one side or both, as is with the case of the largest silicon wafer size as of now, 12 inches. which is polished on both sides before progressing on to the next step in the manufacturing process. Before the 1990s, CMP was viewed as being too dirty. The abrasives used in the process themselves would contain impurities and create particles from the surface of the wafer, which could further attack the wafer and damage the surface. The chemical slurry, which is made out of various corrosive chemicals, can also cause stress cracking and are a major cause of corrosive attacks, which weakens the wafer. These problems could all be solved with the optimization of new technologies which would mitigate these problems. The oxide polishing process, which is used as an alternative to CMP, was the only process in use before the 1990s. No matter the method used in getting the surface of the wafer as smooth as possible, the wafer is now ready to be washed as it approaches the end of being a silicone wafer into becoming a silicone microchip. The wafers are cleaned and dried in order to make sure that there are no contaminants on the surface of the wafer. The manufacturers cannot risk the chance of contaminants larger than 51 nanometers on the surface. Any organic residue that was left on the surface would also be cleaned off. After this, the wafer is sealed in airtight packaging to where the chips are finally made by the overhead carriers that are almost synonymous with chip fabrication plants. The wafer is now ready for the next step in the process, where the wafer would finally enter the realm of usage, where the chips would finally start being etched onto the wafers. Hi, it's Element Daddy 9 again, and congratulations, you made it to the end of the video. Next time we'll be talking about the etching of the chips, so stay tuned guys. Adios! Oh, and don't forget to like and subscribe to my channel. Bye!